Greetings, folks. Welcome. A common application of statistical inference is to use information from a sample of data to say something about a larger population. For example, you might want to test a claim you have about a population mean or a population proportion. As a specific example, let's say we want to test a claim we have about a population proportion. For example, I've always had this idea that I think that fewer than 20% of economics professors mow their own lawns. Of course, a very important concept in economics is the idea of opportunity cost. So if an economics professor knows the opportunity cost of their time, they might be more apt to pay somebody else to mow their lawn so they can spend that time doing something else. To write out this claim as a formal hypothesis that we'll test, we start with an alternative hypothesis, that's P is less than 0.20. In other words, that P stands for the percentage of all economics professors. So my claim is that I think the percentage of all economics professors that mow their lawn is less than 20%. The null hypothesis is that my claim isn't true. So that's written out as P is greater than or equal to 20%. So now we can go through the steps for a hypothesis test. Again, as a reminder, my claim is I think that fewer than 20% of economics professors mow their own lawns. So of course, the first step is to write out the hypotheses that we looked at a second ago. The alternative hypothesis, H subscript A, is that P is less than 0.20. In other words, this percentage is less than 20%. We're testing that against a null that P is greater than or equal to 20%. That's step one. The second step is to set the significance level, which is the probability of making a type 1 error, where we mistakenly reject the null hypothesis when in fact it's true. And again, the significance level is something that we set as a researcher. In this example, I'm going to set the significance level as 0.10. In other words, before I've even started the study or collected any data, I'm saying that I'm okay with there being a 10% chance of making a type 1 error. The next step of a hypothesis test is really the fun part where we go out and do the research. So let's say I went out and I surveyed 100 economics professors and I found that 12 of them mow their own lawns. So if you have 12 out of 100 economics professors that mow their own lawns, that's 12% or 0.12. So now we can use the information from the research, again, finding that 12% of economics professors mow their lawns, to calculate the test statistics. And in this case, since it's a hypothesis test about a proportion, the test statistic is a Z statistic. The formula is Z equals P bar, again, that's the sample proportion from our research, minus P naught. This is a proportion from the null hypothesis. You divide that by the square root of P sub naught multiplied by 1 minus P sub naught divided by the sample size. So now we can take the exact values from our example to calculate the test statistic. You might recall that the sample proportion from our research was 12%. In other words, 12 out of the 100 economics professors that I surveyed claimed that they mow their own lawn. You subtract from that 0.2, that's the value from the null hypothesis. You divide that by the square root of 0.2 times 1 minus 0.2. Of course, that's divided by 100 because that's the sample size. With all these values, you calculate a test statistic or Z statistic of minus 2.00. The next step is then to find the p-value that corresponds with a z-score of minus 2.0. So here I'm just going to show you a standard normal curve. It's single-peaked, symmetric, and bell-shaped. I've put in a line that corresponds with minus 2. And then, of course, the big question is, what percentage of the distribution corresponds with a z-score of minus 2.0? So now to find the percentage of the distribution that corresponds with a z-score of minus 2.0, we go to the standard normal table. And as a reminder, the standard normal table shows cumulative values. So it would be the percentage of the distribution that is less than up to a z-score of minus 2.0. So here's the standard normal table. You see going down that first column, z-scores of minus 3, minus 2.9, minus 2.8, etc. Going across the first row, you see 0, 0.01, 0.02, 0.03, etc. So of course we want to find the percentage that corresponds with a z-score of minus 2.00. It's shown here in red in the very bottom row here. And that value is 0.023. So now we can go back to the standard normal curve and actually fill in the percentage of the distribution that corresponds with a z-score of minus 2.00, and it happens to be just over 2% of the distribution. In other words, if you look at this standard normal curve, of course, under the entire curve, you've accounted for 100% of the distribution, but that part on the left-hand side, that left-hand tail, it's about 2% of the distribution is under that part of the curve. And in fact, that is our p-value that we calculate for this hypothesis test. So now the next step of our hypothesis test is to think about that p-value, again, which was about 2.3%, which is pretty weak evidence in favor of the null hypothesis. Again, recall that the p-value is the strength of the evidence in favor of the null, and this is very, very weak evidence. In other words, our claim is probably true. But before we reject or accept the null hypothesis, we actually have to compare that p-value to the alpha, or the significance level that we set at the beginning of the project. Of course, we started with an alpha of 10%. In other words, we were willing to tolerate a 10% chance of rejecting the null hypothesis when it's true. But with a p-value that we actually found of 2.3%, our p-value is well below the significance level that we set at the beginning of our hypothesis test. So to sort of wrap things up, since the p-value, again, our p-value was about 2.3%, is less than the alpha, or the significance level we set, which was 10%, we can reject the null hypothesis in favor of the claim that I had. In other words, we can say that with a 10% significance level, and based on a sample of 100 professors, less than 20% of economics professors mow their own lawns. Again, that sort of makes sense, given that economics professors think a lot about the opportunity cost of their time, so they're probably more apt to pay somebody else to mow their lawn so they can do things like make videos about applied economic data analysis.